All right. So this is from the 1997. So it's an oldie. So it's a non-conducting sphere. That's important, non-conducting. So we're talking an insulating sphere with a center at C and a radius A has a spherically symmetric electric charge density. Okay. The total charge of the object is greater than 0. So they're just telling us it's positive. They're giving us the value of Q. So that immediately suggests that the charge density, I want to use rho, would be Q over 4 pi epsilon, 4 pi, yikes, I'm in trouble, 4 pi a squared. Let's try all that again, 4 pi a squared. There you go. Determine the magnitude and direction of the electric field at point P, which is distance r, which is greater than a, to the right of the sphere center. So we're talking about right there. Okay. Well, it says determine, so generally that's a low threshold, but for showing evidence. So, the direction is going to be to the right because it's a positive charge density. An electric field points in a direction a positive charge would be pushed. The actual size of the electric field we could just write as Q over 4 pi epsilon naught r squared, without any fanfare, because the whole sphere will act as a point if we're outside the sphere, and it has a uniform charge density. But let's do the steps necessary. If that dotted line that's there was our Gaussian surface, then we would have Q enclosed equal to Q, and the calculation of our flux, E dot dA, will just be a couple of quick steps. First, dealing with the dot product, the direction of the electric field from the sphere is this way, and the direction of the area is that way. So if I were to write this as the sum of E times dA times the cosine of the angle everywhere on the surface, the angle is going to be 0 degrees between the electric field and the area. And since we're equidistant from the surface, the electric field is going to be constant over the whole area. So all I have here is what I need to get out for the area and the electric field. So this will be the flux, or an expression for the flux based on the electric field. So if I want to use Gauss's law, I bring Q enclosed together with the electric flux, and we'll get Q equals epsilon naught E times 4 pi r squared. So E must equal Q over 4 pi epsilon naught r squared. So this answer is A, but I did way more work than they were probably expecting. Question B. Determine the flux of the electric field through the spherical surface centered at C and passing through point P. Okay, so the flux, and this is where I think students will make mistakes, E can't be in our answer. So this will not serve as our answer to that question. However, Q enclosed equals epsilon naught times the flux. So I solve this for the flux. I'll get Q enclosed equal Q divided by epsilon naught. There we go. That's our answer to the flux through point P. All right. Moving down to our next question. A point charge, negative Q, is now placed a distance r below point P as shown above. Determine the magnitude and direction of the electric field at point P. Well, now we have an electric field from the charged sphere in this direction, and we know from the sphere, I'll put a little s there for sphere, this has to be Q over 4 pi epsilon naught r squared. So that's the electric field from the charged sphere, and it's to the right. So I'm going to put in the positive x hat direction. The point charge, so the negative q, is going to generate an electric field that's identical to this, but it's going to be downwards. So q over 4 pi epsilon naught r squared, but negative y hat direction. So that's a contribution to the electric field like that. And they're going to be of equal size because it's equal charges. So our actual magnitude of our field is going to be what you get when you add those two vectors together, which should produce a total electric field like that. Now, these are of equal magnitude, so if you're using the Pythagorean theorem, which is what I would use, you're just going to get a root of 2 in front of these. So our magnitude will be total plus e negative q squared plus 1/2 power, which just means ET is going to be ES and the same magnitude, over 2 of S. So that would be root of 2 times q over 4 pi epsilon naught. And since they're of equal magnitude, I don't think it takes a lot of math to realize that we're talking about the tangent of the angle would have to be equal to 1, so theta's got to be 45 degrees. And providing proper direction, negative 45 relative to the x-axis would probably be a proper way to express that answer. All right, now I've got this weird shape. Now consider 4-point charges, Q1, 2, 3, and 4, that lie in the plane of the page as shown in the, sorry, I gotta read it all, in the diagram. Imagine a three-dimensional closed surface whose cross-section in the plane of the page is indicated. Which of these charges contributes to the net flux through the surface? So that first question, the net flux through the surface, is only about the charges enclosed. So to answer question 1, I would put Q2 and Q3 because Q4 and Q1 aren't inside. That seems like a reasonable answer. Now, the truth is, all of the charges actually affect the flux, but since Q4 is outside the surface, all the flux going into our surface is also exiting our surface. So its total contribution to the net flux is 0. And same for Q1. Now that doesn't mean that they're not affecting the electric field. They're just not affecting the flux. So question 2, which of these charges contribute to the electric field at point 1? It's all of them. They all contribute to the electric field. So I'd list Q1, 2, 3, and 4. Are your answers to 1 and 2 the same, or are they different? Explain. Well, I think I already explained it. They all contribute to the electric field at P1. But Q1 and Q4 don't contribute to the flux because their field lines pass both into and out of this surface. But only Q2 and Q3 originate electric fields or terminate electric fields. So their field lines are passing either out, all of them, or into all of them. So let's go to question E. If the net charge enclosed by a surface is 0, does this mean that the field is 0 at all points on the surface? No. It just means we have equal amounts of field going both into and out of the surface. So you could have strong electric fields going out of the surface in one part of the surface and electric fields going into the surface at other parts of the surface, but the total flux is 0. So all electric field going in is equal by all electric field going out. If the field is 0 at all points on the surface, does this mean there is no net charge enclosed by the surface? Justify your answer. So if the field is 0 at all points on the surface, does this mean there's no net charge enclosed by the surface? Well, the answer is in Gauss's law itself. I mean, if you do the integral, but E is 0 at all points, you're going to get a total flux of 0. That means there has to be a net charge of 0. The law is the law in this case. All right, that's the first question. Let's go on to this question. A sphere of radius r is surrounded by a concentric shell of inner radius 2r and outer radius 3r, as shown above. The inner sphere is an insulator containing a net charge of positive q distributed uniformly through its volume. Spherical shell is a conductor containing a net charge of positive q, which is different from the positive q of the insulator. Use Gauss's law to determine the electric field for the following values of r. The distance of the distance from the center of the insulator. We did one of these yesterday, but I'll take another quick run through it. So if we have a Gaussian surface that is enclosing the region of space that contains our insulator. So let me put something up here that might be visible. I don't know. Let's see. There. So there's my Gaussian sphere. We're looking just at the insulator. This represents the amount of charge enclosed, but it's symmetrical. So I'll have electric field lines penetrating the surface in this direction, and that'll be true everywhere around the sphere, and the area will have a direction indicated that's perpendicular to the surface as well. So our area and our electric field is going to be the same everywhere. Let's start our process based on that idea. So let's do the flux portion first. So flux is going to be equal to the sum of E dot dA. Due to symmetry, the electric field is going to be a constant everywhere on that surface. We just covered the fact that the direction of the area is the same as the direction of the electric field, so our cosine is going to be 0 for all of those as well. That means we can probably immediately drop down to this as a means of writing what our electric flux must look like. At the same time, our Q enclosed is a little weird because we're not enclosing the whole sphere, so it's going to be the charge density of the sphere times the volume enclosed. So our charge density is Q over 4/3 pi r cubed, and our enclosed volume is 4/3 pi r cubed. So we put all these things together, and my Q enclosed cancel out the 4/3 and the pi. My charge enclosed is going to be Q r cubed over big R cubed. So that has to equal epsilon naught times the flux. So Q r cubed over big R cubed equals epsilon naught E times 4 pi r squared. So do a little algebra. I got Q r over 4 pi epsilon naught big R cubed. So that's the electric field. R is less than 1, greater than 0. Now, next they want to know what the electric field is from R equals big R to 2R. That one's pretty straightforward because that's like in a region like right here. And this whole thing just reads as a point charge. So I do think it's important to realize that at the surface, when R equals R, this becomes that of a point mass. So when R is greater than R, but still we're in that region of space, so we get that'll be what we'll use for the electric field. Now, last one, when R is between 2R and 3R, field 0. We're inside a conductor. Electric field is 0. Determine the surface charge density on the inside surface of the conducting shell and the outside surface of the conducting shell. Well, glad you asked. Consider this Gaussian surface. If I can select just there, I'll just try and I'll get it just centered. There we go. That'll do. So if we consider that Gaussian surface, which is located right now inside the conductor, because the conductor has an electric field of 0 always, that means inside this sphere, which I didn't color very good, so let me try a better job so we know what we're talking about here. I don't want there to be any ambiguity. So inside this region of space, which is the volume enclosed by that new Gaussian surface, electric field is 0, which means the charge enclosed has to be 0. That being said, we know that the inner sphere, so this thing right here, we know that its charge is Q, but Q enclosed equals 0. So the charge here has to be negative Q. So if I want to say, what is the Q on the inside? I know Q enclosed has to be 0, but also has to be Q on the inside of the shell plus Q from the sphere. So doing a little math, Q inside has to equal negative Q. It has to. But the outside surface of the conducting shell, well, we know the shell has a total charge of positive Q. But the inside of the shell has a charge of negative Q. So how much charge is left on the outside? Well, what must be on the outside of the surface, so we're talking about right here, I'll spread out all around the outside, has to be a total charge of Q, so Q outside plus Q inside has to equal positive Q, because that was the charge that was placed on the conductor. Well, Q inside is negative Q, so solving this for Q outside, positive Q plus Q. What does that mean for us? Well, we want the charge density. So for D, that's going to be the charge on the inside, which is negative Q divided by the surface area, 4 pi 2r squared. And for E, it's going to be the charge on the outside, so positive Q plus Q, all divided by 4 pi times 3r squared. Those are our two charge densities. Alrighty, fun times.